Hello everyone, am I audible? Hello, can anyone confirm if they can hear me?
Yes, I get
Yeah,
it.
you are.
Yeah, you are.
Okay, cool. So, hello everyone. Hello everyone. Today, moving forward in the series, we have Sasi Mitra from BSMS 2021. He will be talking about Lomb-Scargle Periodograms, which is a really widely used topic in the field, especially by astronomers. So, over to you, Sasi.
Okay, audio check. I'm audible, right?
Yeah, you are audible.
Okay, perfect. So, so let's talk about the Lomb-Scargle periodogram. So basically, the Lomb-Scargle periodogram, basically the idea with it is we are collecting data and there is some periodic signal in it, and we don't know with what period the periodic signal is repeating. And that is where you would use the Lomb-Scargle periodogram to basically find out the period of the unknown periodic signal. So that's basically the purpose. Yeah. Now a periodogram is, so let's just talk about a periodogram first. A periodogram is basically a function that is used to identify the dominant periods of frequencies or in a time series. This can be a helpful tool for identifying the dominant cyclical behavior in a series. So for instance, you are looking at the brightness of a star for a long time, and you can see how it cyclically, I mean, how it changes over time. And if you have a planet eclipsing it, or you have a another eclipsing star, like in the case of an eclipsing binary, or let's say you're collecting data of the brain signals, and you or brain signals or the, I don't know, the heartbeat, you could expect to see a periodic pattern over there, but you don't know what period the signal is repeating. So to identify the specific signal, you could get help of a periodogram. Now, just a quick reminder of the Fourier theorem. So most of you might have seen the Fourier theorem in IDC, but if you didn't, it basically states that any time series, any infinite function or any time series function can be expressed as a combination of sine and cosine waves with differing periods. And this Fourier theorem and the resulting implications of that are what form the basis of trying to analyze this time series data. So before we get too far in, let's just get a brief review of a Fourier transform. Let's not worry too much about the details here. So now a Fourier transform is normally given by this giant formula. It even relates the complex numbers. But basically what it does is if you have a function, if you have something as a function of time, it essentially converts it as a function of frequency, at least in this case. It goes from what we call as a time domain to the frequency domain. Okay, you might have seen it. You might have seen some other applications of it, such as converting a function from position space to momentum space, etc. But here specifically, we are dealing with the Fourier transform, where it converts from the time domain to the frequency domain. Now, and you can write it in short as this fancy f, and you pass in the function f of t, and you essentially get out the capital F as a function of omega, which is the frequency, or sometimes you even see it as whatever function you are passing in, chota f cap. Now, some properties of the Fourier transform that will be held that will be helpful for us. First, that it's a linear function. So basically, when we say a linear function, we just mean that the sum of two, okay, sum of the Fourier transform of sum of two functions is the same as the sum of the individual Fourier transforms of each function. And then you also have something known as the power spectral density, which essentially is the square of the Fourier transform. Now you can see this giant imaginary part contributing to the Fourier transform integral. Now that makes things simpler while integrating, but to get some meaningful insight, we try to get rid of the imaginary term. So that's where we are going to get that's where we are going to square the Fourier transform, and we are going to get the power spectral density. Now the PSD is just a function of the power against the frequencies. So if there's a signal of if there's a signal of a particular frequency in the data, you would expect to see a peak at that specific frequency in the power spectral density. So let's think. So next thing we need to discuss is basically a convolution. So a convolution is, you can essentially think of it as area under the product of two functions for different values of tau. So it's formally defined with this giant formula, but as you can see in this great animation from 3 blue 1 brown, you can essentially imagine it as the area under. So you have this third graph, which is the product of the first two, and you can essentially think of it as the area under the product for the different values of s. It's s in the case of this, and it's tau in the case of our thing. Sorry, it's t in the case of our formula here. Essentially, you can think of it as taking one function and sliding it over the other and getting the area under it. If you want a deeper understanding of convolutions, I highly recommend this excellent video by 3 blue 1 brown. Now, how convolutions are relevant for us here is specifically the convolution theorem of the Fourier transforms. So basically, these two formulas simplify it. This asterisk in the middle, that is a symbol for a convolution, and this centered dot is a normal product. So Fourier transform of convolution of two functions just gives back the product of two Fourier transforms of the individual functions. And Fourier transform of the product of two functions is the convolution of the Fourier transforms of the individual functions. So all of that is some mathematical jargon that will hopefully make things easier going forward. So let's look at a few useful functions. So first we have the sine curve. It's just a periodic curve. I mean, I could have picked any periodic curve, but the simplest of them all, simplest periodic curve is the sine curve. It repeats with a period of 2 pi, which you can change based on the inputs, etc., etc. Now, the next function that we need to talk about is the top hat function. Essentially, the top hat function is that it's equal to 1. Okay, you specify a range A to B, and within that range it is 1. Everywhere else it's 0. And if you try to plot it out, it essentially looks like a top hat if A and B are wide enough in your graph. And the third thing we could look at is the Dirac-Combe function. Now, the Dirac-Combe is basically just a periodic Dirac delta function. And Dirac delta function, for those unaware, it's just everywhere 0, a single point goes up and gives a value. Here the value is 1. Now over here the Dirac-Combe, it's basically every one unit the function goes to a value of 1. Everywhere else it's 0. Now, why do we need these functions specifically? So we need these functions specifically when we are trying to represent real world data using mathematical functions. Now over here in this graph, I have a base signal, like whatever the source of the signal is, it's giving out information in the form of a sine wave. But you are going to observe, you're not going to observe continuously from t is equal to 0 to infinity, right? So to account for, so you're just going to see it from, I don't know, t is equal to 1 to t is equal to 11, for instance. So this green line over here, this green line over here is the data, I mean, is the time over which you are just collecting data. And you don't have any data after that. So the time that we are going to observe, let's just put that as a top hat function. And then within those 10 seconds, we are not going to record data continuously. Like, right, it's a I mean, you are looking at a digital signal, it's going to have some gaps in the middle. So every instance that you are collecting a sample, and collecting a sample, you are recording the data, you could put that up as a Dirac delta comb if you are collecting data evenly. And essentially the actual data collected, it ends up looking like this, just a bunch of points over which you are doing best fits. Now obviously in realistic data you'll even have noise, but over here I didn't over here we were ignoring the noise. So basically everywhere it's zero except for the times where the Dirac delta function and the top hat are equal to 1. So that is just a product of the three functions that we saw: the underlying periodic signal, the observation times top hat, and the data sampling times delta cone. So now you can see how the convolution theorem could be helpful. Let's just take a short break for questions before moving forward, if there are any. Okay, I guess we can move forward. Okay, so let's talk about the Nyquist limit. So basically, the idea with the Nyquist limit is that if you have collected data, if you have collected data with a given sampling frequency, you cannot go back and calculate every single you cannot possibly recreate every single frequency, I mean, every single periodic signal with it. Like there is an upper limit to what frequency the periodic signal can have given a sampling rate. So what is a sampling frequency or a sampling rate? So basically it's a measure of how often you're taking the observations. Basically f naught is the sampling frequency. It's just a 1 by t, how often you're taking the observations. You can think of it as you can think of it as the frequency of the delta cone. Now uh, the Nyquist limit states that the frequency that you can recover from the data are just the frequencies that are between plus f naught by 2 and minus f naught by 2. So if you have, let's say you have a sampling frequency of 3 hertz, you cannot get anything more than 1.5 hertz from that. That's basically what the Nyquist limit says. Now let's just try to understand why this is. Now there is a mathematical explanation, but let's try to look at some actual data, I mean, simulated data rather. So if I'm taking observations at the Nyquist limit, so over here I have a periodic signal. I have a periodic signal, and the periodic signal has a frequency of the Nyquist limit. You can see that all the sample data is just ending up at zero. It's coming out at the same value. Now, if I had collected this data, in the lab, you would think that okay, there's no signal here. It's just it's just zero everywhere. But as you can see, there's an underlying signal. That's definitely not the case. Now let's take something at a frequency that's greater than the Nyquist limit. So over here, the yellow, okay, this is a bit of an ugly graph, but over here, the yellow line is basically our actual signal. Now I've sampled data at a frequency that is greater than the Nyquist limit. And you can see that, okay, every once in a while, you have some points that are not zero, that are not constant everywhere. But the issue is I can find another signal that fits the data. Like it's not the date. I mean the signal that you can. I mean the periodic signal that you can find to explain the data you have collected. It's not unique beyond the Nyquist limit. There's a specific formula for that will not go into, but you can look up the sources referenced at the end of that I'll share at the end for further reading. And so basically this should give you an idea about why we should worry about the Nyquist limit. Like at some point the observations you are taking, you can start having multiple frequencies that explain it, and it makes no sense to, and your data essentially just becomes meaningless. Okay, before we move forward, let's just take a second or two wait for questions. Okay, no questions. Great. Okay, so from from everything that we've discussed, we could technically derive the Schuster periodogram, and here are some details for the interested people to try it out. But let's not stick our head too much into the formulas. So basically the idea with the Schuster periodogram is that it's a variation of the discrete Fourier transform. Now the discrete Fourier transform, the way it's calculated and all, you can look at it in depth. But basically, here's the formula for the discrete Fourier transform. It's a summation. It's a summation, and you have a complex component and you are taking a summation at each point each point that's being sampled. Now the frequencies that you can detect is just going to be between 0 and the Nyquist limit, and we can sample that on delta f is equal to 1 by n delta t. N is just a number of observations that you have, and then just making a simple okay, and then you can just make a simple substitution and just get this guy g hat k, which is essentially, which you can think of it like the discrete Fourier transform calculated at each sample frequency. And then you are just taking the power spectrum of that. You are just taking the power spectrum of that. So, okay, sorry. Okay, so let's not worry about too much about it, but here's the final, classical periodogram that you get. PF is equal to 1 by n, and you have this entire giant thing, which you can just think of it as a discrete Fourier transform. Now, basically, so that gives you your Schuster periodogram. Now, the big thing to think about here is that the Schuster periodogram, it's not the power spectrum directly. It is scaled by 1 by n. You don't know what exactly the power at each frequency is going to be. You just know where the peak is, not the value of the peak. So that's the Schuster periodogram or the classical periodogram. Now, the limitations of the Schuster periodogram is that the formula comes from the discrete Fourier transform, and it inherently assumes that the sampling rate is evenly spaced. Now, this is not necessarily the case in real world data. Now, astronomical observations very often end up being seasonal, and due to weather conditions, you don't know when you might be able to take the next observation. You can't always get consistent observations. The sampling rate is not going to be evenly spaced. So because of that, you cannot. And aside from that, another issue is when you're taking an observation, you're also going to have some noise associated with it, and there is no way for the Schuster periodogram to account for the noise when predicting the period. So let's before okay. Hang on. Okay, before going forward, okay, hang on. Yeah, before going forward, do we need to stop and discuss anything? Any doubts? Okay, let's go forward then. Now, Lomb and Scargill, they were two scientists who noticed something, who basically tried to generalize the Schuster periodogram back in the 1970s and 80s. Basically you have this. Let's again not worry too much about the formulas, but basically you have this nice function, which is again just a sum of sine and cos waves, and you have a few values, a, b, and tau. Now, Scargill showed that you can choose a unique set of values a, b, and tau. Now, a, b, and tau are specifically arbitrary functions of the frequency and observing times, but not observed values. So basically, the values that you measure, they don't affect the choice of a, b, and tau. Only the yeah, they don't affect the choice of a, b, and tau. Only the frequency and observing times. Now, Scargill showed that you could choose a unique set of values where the periodogram reduces to the classical one in equally spaced observations. First thing. Second thing, the periodogram's distribution is analytically computable, and the periodogram is insensitive to global time shifts in data. Now, a better way to sort of think about this is that you're essentially trying to fit periodic waves of various frequencies and then trying to find the best fit values for those frequencies and then getting the power and then getting their power. And that's another way to derive the Lomb-Scargle periodogram essentially. Now, variants of this LS periodogram, they try to fit a different periodic function. Now, the original Lomb-Scargle periodogram, it tries to fit periodic waves like a sine wave to the data, but variants, they try to fit a different periodic function like a box function. Now, depending on your data, you can choose this function accordingly. So before going forward, let's just summarize some important things important takeaways. Real world data is unevenly sampled, it's not continuous. Second thing, because of the Nyquist limit, you have an upper limit on what frequencies can be estimated from a given set of data. Third thing, a periodogram is a power spectrum estimator. It tells you only where the peak is, but the what value it gives at the peak, it's not really helpful. Now, the Lomb-Scargle periodogram essentially tries to fit various periodic functions to the data and then calculates power at that frequency. And depending on the signal that you're looking for, you can change the type of periodic function that you're trying to fit to get a better estimate for the period of the signal. Now, all of this mathematical discussion is meaningless. Nowadays, coding languages like Python and MATLAB already have all of this implemented far better than we could try. So let's just go to Google Collab and download some data from a TESS mission and try to find the first ever planet that was observed by TESS. So, okay. I believe this Collab notebook is not shared. I'll just drop it in the chat. Okay, so okay, so first let's install the light curve library. I'll just refresh it so we can start from scratch. Mm. Okay, let's not worry too much about the first part. The first two parts, I'm just changing the theme so that the plots come out looking nice. For that, I'm just using a different library called Jupyter Themes. Let's not worry too much about it. Uh, okay, so the first thing that I do is I install the light curve library. Light curve library. Light curve library, it's just a fancy library. It's a fancy Python library that has been written by people smarter than I to basically deal with deal with astronomical light curves from end to end. So you everything from downloading the data to everything from downloading the data to coming to the final analysis. There are functions for everything. So that's why we need to install the light curve library. And here it's already installed. Nice. Now, similar to the light curve library, there's also the Astropy library. Again, Astropy library, it has all sorts of nice functions to deal with units, to deal with time, to deal with time series data, etc., which makes things really nice for us. So let's just import the necessary libraries. And okay, so we need to search for the first thing that we need to do is we need to search for the specific piece of light curve that we need. TESS is looking at all sorts of objects, so it'll have hundreds of light curves for hundreds of observation runs. We just need to choose the specific one that we need. And light curve library has not just the TESS mission; it also has the Kepler mission, the K2 mission, etc. So to worry about that, we have to specify what exactly we are looking for. And first we search and we get a search result, and we are just taking the first item from the search results, which corresponds to the first observation. And the PDSAP flux essentially refers to how they pre-process the data and do it for us. If you look at the raw light curve, it's going to have a lot of instrumental errors that need to be accounted for. All that, let's not worry too much about it. And again, you have methods to like get rid of outliers and all that. And finally, let's just take the flux value, which just comes from lc.flux, and time values, which come from lc.time.value. And let's and again if and again time is a very complicated thing to program, so let's just convert all of this time values to units of jd or Julian date. Basically, the idea with Julian date is it is some number that represents time, and every 24 hours it increments by 1. And and when you scatter whatever you've observed, and this is essentially what you get. Now it's a bit weird because you have points all across the place. The data is not evenly sampled. It's not evenly sampled. It's a bit off, but we have something to start off with. Now, within all of this, let's look for a planet in this periodogram. So for that, we import Lomb-Scargle from astropy.stats. Astropy.stats is a sub-library within Astropy. It has a bunch of statistics functions. And let's just import Lomb-Scargle from there. Now for Lomb-Scargle, we need to pass in the time values and the flux values. We need to pass in the time values and the flux values, and we just say Lomb-Scargle time. Okay, we give it the time, and we give it the flux, and we just tell auto power, and that essentially gives us the frequency and the power of the periodogram. And running that, here is the plot that we get. Now, if you look at this, it's not a particularly great fit. Like we are getting that we have something at like the frequency near 0. Now, if you explore further, it comes out to be that you have a period of maximum estimate coming out around 0.0006 days. That makes no real sense. So that's probably an indication that the curve that the Lomb-Scargle is fitting, the periodic sine curve, is probably not a great thing. Now, if you know how the exoplanet, if you know how an exoplanet transit curve looks, it looks an awfully lot like a box plot. So let's use a variant of the Lomb-Scargle called the Box-Lee squares, or the BLS, and let's use this to find a period and let's use this to find the period of our data, of our signal rather. So again, I have an array of time values and I have an array of y values. I'm just making a model called Box-Lee squares, and I'm giving the time, and I'm specifying it has a unit of day. And along with that, I'm also giving it the flux values as y. And then periodogram, I just tell it model.autopower, and then we just plot the period and the power of the periodogram, and this is what we get. And looking more specific, and if we look at this, we have a peak just a bit after 6 days, and we can see that the maximum power is happening at 6.27 days specifically. Now that we have a possible period, we need to like fold the data to see if there's a signal at all there. So now what does folding mean? So you can imagine the x-axis to be represented by the equation x is equal to some quotient q times t plus r. The r is basically making up our phase. Now ideally all the values at a given phase will have the same value in the periodic signal. So you can imagine how, despite the value of n, sine of 2n pi is always going to be equal to sine of phi, right? Sine of 2n pi plus phi is always going to be equal to sine of phi. Just like that, at the periodic signal's value at a given r, regardless of the value of q, is going to be the same. Now, Astropy has a function called fold, which we can use. Again, I have my x data and y data, x data of time, y data of flux, and then I'm just taking I'm taking all the time data and I'm just converting it into a time object. I'm converting it into an array of time objects. So I have x data here, and I'm specifying the format is JD, and I'm giving it the scale UTC. And then I create a time series object. Now a time series object. Now the function fold that I mentioned, it is a specific function of the time series. Now we are dealing with the time series data, so let's just create an object of time series, and we give it, and we tell that the data is the flux in millijansky. The unit doesn't really matter, and we give it the date. We give it tell the flux. We have flux in millijansky, and we are giving the time as all the time values. And we just tell fold, and we just ask it to fold, and we specify the period to be whatever period of maximum power that we found. we just give it this value. We just give it that value as period, and we just scatter the plot over the periodic symbol. And now if you notice, you find that there's the characteristic dip of an exoplanet. So you can imagine this: the telescope is looking at the star throughout all of this period, and it's not noticing any major fluctuations in the brightness. And when it comes here, the brightness has suddenly come down for a while, and then after a while it goes up again. So that is essentially what this plot tells, and you can take this dip and analyze it further to find more details about the exoplanet that's been detected in this transit. This is the classical. I mean, this is the famous famous exoplanet transit curve. And okay, and since I mentioned light curve has methods to deal with it end to end, light curve itself has a few ways to the light curve module itself has a few functions to do all of this for you and make things simpler. So you can directly search and make a scatter plot of the clean data, and then you have a simple function to just take the periodogram. You just say light curve to take a periodogram and specify box least square method and just ask it to plot that, and it just plots it for you. And you can ask it what's the period at maximum power, and it gives you the maximum power as well. And then you can just tell it to fold. You can just tell it. Sorry. Yeah, you can just tell it to fold over the data, and it'll show you the folded curve as well. So yeah, that is basically the periodogram and how it is used by astronomers to detect periodic signals in astronomical data. I'll stop presenting now. We can open up for discussions, I guess.
Please feel free to ask questions.
Hello, Sasi.
Yes, go on.
This Nyquist limit is a characteristic property of what? Is it something that we arbitrarily set?
No. Okay, Nyquist limit, it's a property of how often you're collecting data. Okay, the Nyquist limit is basically an issue that comes up with the way you collect data, right? So if you're collecting data with a specific frequency, like once every millisecond, okay, then ca- okay, if you're collecting data once every millisecond, can you really expect to find a periodic signal with a period of once every half a millisecond? No, right? The periodic signal is undergoing an entire cycle, undergoing like 2 cycles between 2 points you have collected. So basically, the idea of the Nyquist limit is that you can't okay, if you're sampling at this rate, then you're going to have an associated Nyquist limit, and you can't, no matter what mathematics you do, you can't detect a periodic signal with a frequency that's greater than the Nyquist limit. I hope that makes sense.
Yes, got it, got it.
Hi, Sasi. So I had a question in this regard regarding the Nyquist limit itself. So suppose you have 7 sample points.
Asma, your voice is breaking.
Is that okay? Is it fine now?
Yeah, it's fine now.
Yeah.
Yeah. So say you have certain points and you sampling it. I mean, as in you're fitting it, and you have certain limits or certain graphs which best fits it, and you know that these are within the Nyquist limit. So which one would you choose? Like, how to determine that this particular plot or this particular thing would be the best one amongst two, say, plots which is in within the Nyquist limit?
Okay, if you have something within the Nyquist limit, that again comes down to what kind of signal you're expecting to see, right? I mean, if I'm looking at an eclipsing, if I'm looking at an eclipsing binary and I have a best fit of a box plot, that that would sort of make sense. But then again, it's hang on, sorry, that's a bad example. Okay, if I'm looking at a eclipsing binary, so that's basically when I have a star and another star is going in front of it. So during this short time when the two stars are there, you're going to have a different brightness value, and you would expect to see a box plot of a periodic signal. And somehow I get a sine curve that's the best fit. Both of them are good best fit curves, but like at this point, it would come down to what signal you're expecting to see. So I
Right. So
hope
you're
I
telling me that
interpret.
yeah. So you're actually telling that it depends on what you want to observe, right? What the
Exactly.
actual thing is. Yeah. Yeah.
Exactly. It depends on what you're trying to observe and what you're expecting to see.
Okay. And I don't know, like if I missed it, but can you tell me why does such a limit exist? Like, the mathematically, why does this, if that doesn't complicate stuff?
Mathematically, okay, give me a second. I'll try to find a graph. Okay, the Nyquist limit, it is best understood for evenly sampled data. There's a very confusing discussion for unevenly sampled data. But basically, the idea with it is the simplest way I can show why to worry about it is here. Not here. Sorry, here. I have multiple frequencies beyond the Nyquist limit that fit the same data. That is one way to see why to worry about it. Another way to see why to worry about it is okay. Here's an extremely great review paper that's talking about the Lomb-Scargle Periodograms. And okay, so basically, like we discussed, data, you can think of it as a product of. You can think of it as pointwise product. You can observe data as just a pointwise product of your underlying signal and a Dirac delta comb. So if I take the Fourier transform of that, let's say over here I have a Gaussian signal, and I have a window function which is just how often I'm taking data. That's a Dirac delta comb, and with that I get a different Gaussian as the Fourier transform, and for the window function I get a different Dirac delta comb. Now, if you look at the convolution, it basically what happens is that at each uh, at each comb you're going to have a different Gaussian as the Fourier transform of the observed data. Now, at the Nyquist limit, you can see that basically you can see that the Gaussian from each observation is going to start overlapping with the next one. So essentially, it makes no sense to look at frequencies that are greater than f0/2. That is basically a bit more advanced method of thinking about it, but I wanted to avoid this because I didn't know how much the audience would know Fourier transform. I hope that
Okay.
made sense.
Yeah, that makes sense. Thank you.
Yeah, Sasi, can I add one thing?
Yeah, go on.
Yeah, Asma, when you asked about that, the previous question that you asked, did you mean that how can we see the different light curves and then if all of them are within the Nyquist limits, how can we detect? How can we decide which one is better or not?
Yeah, kind of. So, say, in the graph that he showed, we had certain points, and we already,
Yeah.
say you have, 2, 3 plots which matches the curves, like which matches the sample points, which are within the Nyquist limit. So, like, how exactly do we determine which plot exactly matches with what we need? So, how to determine that?
Can you repeat the last part? Like, are you saying that all of them are already within the Nyquist limit, and then
Yeah,
you want to decide which one is like the best one?
yeah, how to determine which suits our, requirement.
Okay, so like the answer that Sasi answered that it depends case by case. So it's like for just by seeing the light curve, there a lot of information can be retrieved. So there are like one or two examples. If Sasi, you don't mind, can I just share a screen for 2 minutes?
Yeah, sure, go ahead.
Yeah. Okay. Just give me a second. I'll share my screen and then to be ready.
While Archit is preparing his screen share, any other questions we could discuss quickly?
Is it visible?
Yes, your screen share is
Yeah.
okay.
Yeah. So Asma, like you can see, I will show you one example. So this is some particular star with some ID, like it has been taken from the test data. Okay. So you can see over here that this particular light curve that we are generating using the light curve module that Sasi just now discussed. So over here you can see that the amplitudes are also changing as well, and the frequency is kind of constant, right? So from over here only you can see that the star that we are talking about is like evolving, like some features inside the stars are evolving. Because of that, the signals, like the photons that is coming to the telescope, that pattern is kind of sinusoidal, like it's changing. So with the help of that, you can tell that the x-axis is just the time in days, and with the help of that, you can directly tell that how fast the star is rotating, something like that. Similarly, like there are one or two. This is just simple sinusoidal pattern kind of thing. There are one or two more. Just a second, I'll show. Mhm.
Hello, am I audible?
Yeah.
Okay, in the chat there was a question, does it tell anything about the amplitude of the wave? So are we talking about we are talking about the underlying periodic signal, right?
Yes.
Okay. Now from the power spectrum itself, you can't really. I mean, from the periodogram itself, the power spectrum you get, it's just an estimator. It's not the actual power spectrum. So from the periodogram itself, you can't do anything. But after that, you can fold the database. Or you can do what's called as phase folding. Hang on, I'll get back to the Collab notebook. Okay, yeah. So basically, the idea with the phase folding is that uh, sine to a okay. So I have a periodic signal. It happens every 2 pi. It happens with a period of 2 pi, and so basically, the idea with phase folding is that the value of the periodic signal at a given phase is always equal. So sine phi is always equal to sine 2n phi, regardless of the value of n. So since you calculated the period from the periodogram, you just take the maximum value in the periodogram, and then you plug it into Astropy's fold function. It folds a time series plot for you, and then it generates a phase plot. And from the phase plot, you have a pretty good idea of what the function, I mean, what the periodic function looks like. Now you can do fitting onto this data, the folded data. So over here, you don't have time on the x-axis, you have the phase. You have phase versus flux. You can do more advanced fitting on this to find more properties like the amplitude and all that about the folded data. I hope that answered the question. Okay, cool. Thanks.
If there are any other question, please feel free to ask.
Yeah, also, one more thing. Could you break down it for me? Suppose if you have a wave which is like a summation of two sinusoidal wave of different frequency, and then uh, you try to get the power spectrum of it, then will you get the same amplitude of that spectral or the power spectral density, or will you get a different? And if you get a different amplitude in the power spectrum density, what does that signify? When do you get a different amplitude of power spectrum density?
Okay, from my best understanding, the amplitude and the power spectral density, it tells you, it basically shows how strong the frequency and how strong the signal at that frequency is. And then, okay, but in specifically the periodogram, the power that you're getting, it's essentially meaningless. It just tells you what is the it just tells you what the strongest frequency is, not it doesn't imply anything further about the importance of the frequency or anything. So it's just we are worried more about like what frequency gives the maximum rather than what the value of the maximum is. Now, what exactly the maximum value in the power spec and PST tells, that is something I think Archit is better equipped to handle.
Yeah, should I explain a little bit on this?
Yeah, yeah. Can you like in a collab as well that what are the two different cases when you have the same frequency but the power density amplitude of both frequencies are different?
Yeah, so see, the thing is, when we are looking at a particular light curve or any frequency, sorry, the flux versus time graph as Sasi showed. So the graph that Sasi showed, can you go there one, Sasi?
Okay.
The one which had kind of the pi minus one example that you showed.
This one.
Yeah, exactly. So over here, why you are seeing this particular dip. So in terms of in astrophysics, basically I can tell that since this has a U shape, it means that there would be a particular pattern, or there would be a particular, I would say, spot or something which is stopping the photon to come to that particular telescope from that star. That's why there is a dip in the light curve. So it means that apart from this particular U shape, everywhere else it's kind of flat. It means that uh, other than this particular pattern, everything else is kind of regular. So when it means that you have a around, let's say the frequency corresponding to that flat line is around, let's say, 1 hertz or something, or maybe let's say 100 hertz. So if that 100 hertz is constant, suddenly there will be a different frequency corresponding to that U shape. So when you will be finding out the Lomb-Scargle periodogram of this particular curve, this particular light curve, then what will happen? You will find out a peak corresponding to this particular, what do you say, the U shape. Now, if this U kind of shape is repeating at particular time intervals, then it means that it's not just some random. Okay, so in it, okay, the case that I just now discussed, that case corresponds to some random sunspot or something like that. That's something that just stopped the flux from coming to us. But let's say there is a planet or something like that, and that planet is rotating, is revolving around that star. So then this particular pattern will be kind of regular. Then the frequency, the highest frequency in the Lomb-Scargle periodogram, that will correspond to the time period of that particular planet. Correct? So you can think it in that way. Now, if we talk about the power spectrum, so there is something called wavelet analysis. If we perform, it is another tool similar to Fourier analysis. It takes Fourier analysis and use the convolution that Sasi discussed as well. When you plot the power spectrum, basically power spectral density versus the time plot, then the peak in that particular power spectrum may or may not be same as a Lomb-Scargle periodogram. So if that particular peak will match the Lomb-Scargle periodogram only when this kind of pattern is regular. Means it might be because of some, uh, let's say, moon is coming in between the earth and the sun. So then when you will see the light curve of our sun, there will be a kind of pattern, this U kind of shape, which is stopping the flux when lunar eclipse is happening. Then that particular peak in the power spectrum will match with the peak of Lomb-Scargle periodogram, and it will tell us about the revolution period of our moon. In the similar way, if it is just because of some spot or something, then we know that sunspots or these things are not that regular. It it depends completely on the which star you are looking at or what is your source. So then that power spectrum peak and the Lomb-Scargle periodogram peak may or may not match, but it won't show anything concrete. Is it clear, Shivam?
Yeah, sort of.
Okay,
Great.
just a second. I'll show one very small thing. So you can see this. So you can see clearly that there is no as such a very nice pattern on this. Okay. So but there are very high peaks that are going above, right? So these high peaks correspond to the solar flares that we call solar flares, because in some particular points there are
So
some
you're
random.
talking about flux or power?
I'm talking about the flux.
Okay.
Yeah. So the this is like flux versus time plot. Just see the above plot and I will explain the below one. So in this case, it's pretty noisy data. As you can see, there are no pattern that is getting repeated between the 1630 and 1650 or so on days. And there are some random peaks. So that random peaks are coming because of solar flares. But we know that again, it is very unpredictable, right? It's not any regular phenomenon. Then this particular Lomb-Scargle periodogram peak will not match with the power spectrum peak that you asked. So because it is not a, because data is very noisy and all. Yeah.
So it's like a two-way verification that it's the like you're studying the correct system, so as to say.
Can you repeat once? Your voice is a bit slow.
Yeah, it's like a two-way verification that you are studying, like you are looking at the right planet or whatever obstacle it is.
Yeah, exactly, exactly.
Okay. Yeah,
Yeah.
good.
So there is like exactly, that's a very good point. So earlier, let's say if a star is rotating very quickly in its own axis, then one particular spot might stay for more than one period, right? So then you will be seeing that particular spot itself, that pattern, the U shape in the flux versus time curve, corresponding to that particular spot again and again. But in that case, you might think that this is coming uh, because of some planet, and but that is wrong. Then you will have to do this two-way verification thing with the help of this Lomb-Scargle periodogram as well as the power spectrum, because we know that if it's a spot, then your Lomb-Scargle periodogram will have multiple peaks which would be closer to each other, and power spectrum peak will not very nicely match with the Lomb-Scargle peak. But in the other case, if it is a planet or something like that, then it will match properly because it's very regular phenomenon. Because planet revolution period will not change that easily.
Okay.
Yeah.
Thanks.
If there are any other question you can ask, otherwise we can wrap up the meeting. Okay, then thanks a lot, Sasi. Thanks everyone for joining, and we will be looking forward in our next meeting where uh, a new speaker will take a look into a very nice topic again. So thanks a lot, everyone. I will stop the recording now.
Thanks, Sasi. Great talk.